Hello, this is a live demo of our seam carving application done by Team 19. First, we'll show our GitHub repository page, where as you can see under the Actions tab, we've implemented the CI/CD bonus requirement. This CI/CD script will just ensure that every commit will be able to build and generate the executable files. If not, it will be indicated here that it failed. So for the live demo, we'll use a freshly cloned version of our repository, which includes 6 Python scripts, which is all our source code, as well as this one batch file, all setup.bat. If a user wishes to generate the executable files by themselves, they can run this batch file, which will make use of a portable version of Python, which is here. As you can see, it's only 30 megabytes, and it will make use of that to generate the executable files. The executable files after running this batch file will be automatically placed inside SeamCarving app folder. So inside this folder, there's also an images subfolder, which as you can see here only has one input image, and all the output images will be placed here as well. So now let's start. We'll run the SeamCarvingApp.exe, which will make use of all the other executable files as well. So first, we'll do dynamic programming. We'll choose the input image. We'll name our output image as test1. Well, in interest of time, we'll cut only 5 seams. We'll do it vertically. Then we can also show the step-by-step, which I'll enable for this version, for this dynamic programming. For the visualization, you can see here, there will be the active seam will be shown by a red line, which is the lowest path. And then the user can just press any key to go to the next carving, as you can see here. And this will, since we've chosen 5 seams, this will be done 5 times. The lowest energy is changing since it's being carved. And once it's done, the output image will be saved inside images as test1. And a comparison.jpg will automatically be generated, which will show a direct comparison between the original image and the carved image. As you can see, since we only carved 5 vertical seams, there's a 5 vertical seams difference. Next, we'll show the greedy algorithm. So for greedy, the steps are the same. We choose the input image. We'll indicate the name of the output image. And we'll cut 5 seams, but this time we'll do it horizontally. And then we'll skip the visualization step. The greedy algorithm is much faster, as you can see, and the same. We can check the comparison.jpg to see that 5 horizontal seams will cut. Next, we'll show the graph cuts. So the graph cutting is much slower, but the steps are the same. We choose the input. We'll choose the output name. Interest of time, we'll only cut about 3 seams. We'll do it vertically. Since the graph cutting algorithm is the slowest, it takes quite a while, but after that, the steps are the same. It generates an output image, and you can see that we have carved out 3 vertical seams. Finally, we'll show the live resizing tool, interactive resizing tool. We just need to give it the input image. Then we'll open up this window where we can use the sliders to choose how many seams to carve. We'll cut just a little bit. So here we'll be carving 4 out. Then once it's done, we can save the image and we can continue if we wish, or we can just quit. So once we quit, we can go back to the main menu. But as you can see, we've saved from the interactive carving. We have this interactive result, which we saved after carving just now 4 vertical seams. So as you can see here, compared to the original, it has carved out 4. And that's the end of our demo. Thank you very much.
So we are Team 19, and here's our assignment 2 submission presentation. Here are our group members. So starting off with 2A part 1, to show the number of possible seams growing at least exponentially in M, we look at how a vertical seam moves through the image. A seam picks 1 pixel per row, and from any pixel, it can move at least 2 valid pixels in the next row. Each pixel at the edge can always have at least 2 options. So as the seam goes down each row, the number of possible paths keeps doubling. When you stack this doubling over many rows, the total number of seams become exponential in the height m. And since you have more than 1 starting column in the top row, the total number is even larger. That is why the number of seams grow at least exponential with m, and why we need dynamic programming instead of checking all seams one by one.
The disruption of a seam is defined as a sum of the disruption of its pixels, which means that the total seam cost can be built incrementally. This additive structure allows the problem to divide into sub-problems, finding the minimum disruption of any seam that reaches a specific pixel. Each pixel seam cost depends only on the best cost from the pixels directly above it. Next. We define Mij as a minimum disruption of a seam from the top row down to pixel ij. So this is a formula behind it. Each value of the Mij depends only on the solution to smaller subproblems, which create the overlapping subproblems and optimal substructure, allowing us to compute seam cost bottom up and extract the seam with the smallest total disruption. Thus, defining seam disruption as a sum of pixel disruption directly enables a formulation where subproblems compute the minimum seam cost to each pixel, and combining all these leads to the minimum disruption seam.
Okay, so now we're talking whether divide and conquer method will improve the efficiency. Sober filtering is already has a time complexity of ON. It's a 2D convolution with a fixed 3 by 3 kernel. So the cost will be equals to O times MN, which is optimal because every pixel must be processed. Divide and conquer cannot reduce the work, as splitting the image leads to recurrence like merge sort, where Tn will be equals to Tn times n over 2 plus Fn, which is the same as On log n. This is worse than the original On method. The key divide and conquer tricks do not apply. Pre-sorting used in counting inversions is irrelevant because pixel cannot be rearranged. Reducing subproblems using Karasuba or Strassen does not apply, as convolution cannot eliminate recursive calls. Fast Fourier transform, or FFT, a DNC algorithm, helps only for large kernels. FFT convolution will have a time complexity of O(n) log n, which is not beneficial for 3 by 3 kernels like Sober. So in conclusion, divide and conquer does not improve efficiency for Sober filtering, and the direct linear convolution is already optimal and has no exploitable structure for divide and conquer speedups.
For question 3, the greedy algorithm does not provide visual results that are comparable to dynamic programming. DP checks all possible seam paths and choose the one with the lowest energy. This helps to avoid cutting through important objects or strong edges. Greedy, however, only looks one row ahead. It picks the lowest energy pixel for that row, which might be a good local choice but leads to poor overall results. Next, we can see this in the 3 scenarios. For landscapes and texture images, DP removes seams smoothly, while Greedy keeps cutting in one area, which causes jitter or bending. For strong foreground objects, DP avoids cutting through important objects, while Greedy may cut right through them, causing tearing. For geometric shapes or straight lines, DP only bends lines slightly, while Greedy repeatedly removes seams from the same spot, creating severe tear or collapse. Next. Lastly, Greedy has a compounding error. Once it cuts a bad seam, it creates artificial edges that make future seams even worse. DP avoids this because it always recalculates the best global seam each time. In conclusion, in terms of visual quality, Greedy cannot compare with DP as DP consistently produces smoother and more natural looking resized images. Thanks.
For the time and space complexity between DP and greedy algorithm will produce the same carved image quicker while using less space due to the way it finds the lowest energy seams. This can be seen from the find vertical seam greedy function, which takes a time complexity and a space complexity of OH. This is because it only needs to check the area around to determine the lowest energy pixel. But due to the dominating complexity of other functions, the total time and space complexity of the greedy algorithm will be the same as the dynamic programming algorithm, which is O n times W times H, with M being the number of seams needed to be cut from the image, and W and H being the width and height of the image. Next.
So for possible improvements, we took a look at our dynamic programming script, since it's the most optimal, but just slightly slower than the greedy algorithm. The main reason for this is due to how the DP implementation stores the entire energy table, and this table is a huge matrix of 64-bit floats. So an alternative improvement is to simply separate the energy calculation from the path reconstruction. This is done in two main steps. First, we calculate the minimum energy from O width space. Then we store the path information in a separate width times height integer matrix. Each integer in this integer matrix will indicate the direction of the cheapest path for the pixel above. For example, a -1 will indicate the top left, a 0 will indicate right above, and so on and so forth. So theoretically, this will result in about 4 to 8 times more space efficiency, hence a faster runtime. So maybe the DP algorithm could be almost as fast or maybe just as fast as the greedy algorithm. That's the end of our presentation. Thank you for your time.